So yesterday we left off after regression, after seeing the first few examples where you can still obtain a posterior distribution in a manual way with the tedious calculations, which is nice for something real small, where you still want to understand how information is transferred from your prior distribution and how this is interlinked with your data information and gives you in the end some Bayes estimator, some posterior distribution, which we said will, for finite sample sizes, be biased unless you choose an inference prior or a reference prior, which allows you to obtain this similar scenario to maximum likelihood. So, Bayesian models are not about just simple stuff. If we could do all this stuff by hand, it would be easy enough, and we wouldn't have to talk for another 2 hours about computation. So no worries, I won't talk for 2 hours about computation, just in case you want to run. It's okay, you can stay. I will let you do a lot of computations today, but I want you to understand a little bit what's happening behind these algorithms, how these models are actually built when they are getting more and more complicated, and how this is actually added in the Bayesian paradigm. And therefore, we will talk about directed acyclic graphs as the first thing to start out, because this is a very nice way of visualizing Bayesian models in a natural way. So this is basically the scenario we have had yesterday. Y now is our data. You can see this is the only one which has a square around and not just a circle. So everything that has a square is something which is more or less fixed during the inference. This means Y is the data we observe, and once we have observed it, it's more or less fixed during the inference. And then we have this MLAB. These will be referred to as the hyperparameters. So this is the coefficients, the parameters which we are setting for the prior distributions. We were talking about how to choose these parameters for the prior distributions yesterday, when we were thinking about how does this transfer information into our model, how can we translate patients from a previous study into a prior setting for these hyperparameters, or what would be non-informative ways of choosing these things, like making the precision super small, making the variance super large. So this is the choices we make. And then there's the ones in the circles. And the ones in the circles are the ones which will get posterior distributions. So these are our parameters of interest, let's call them, the ones which we want to do inference on. So this would be a normal distribution scenario where we're not just focusing on the mean of the underlying distribution, but also perform inference for the precision simultaneously. And therefore, we have this one part where the normal distribution prior happens for the parameter of the normal distribution for the data Y. So watch out, Y has a normal distribution with a mean mu, and mu itself has a prior which has a mean of n and a precision of L. And again, Y has a normal distribution. This is the likelihood. We want to learn about its precision, lambda, and this precision lambda itself has a gamma distribution with parameters A and B, as we were discussing yesterday. So this is where we start out. And from this point, we want to think about how to do this simultaneously. So this is the mathematical model behind it. Again, I try to stay true with the color coding. So blue is the likelihood, red is the priors. You can see now that it gets more complicated, and I did it wrong because this should be blue. But yeah, I'm trying my best. And then the blue, of course, I can't even pretend to be colorblind because that doesn't work in. So the mu and the lambda should be the ones having priors on, and the y as the data distribution is the stuff which should be blue and which is the likelihood in itself. So how to learn about these things? Doing this simultaneously with a so-called normal gamma prior would require that we now would use a bivariate distribution. Bivariate is, of course, a lot more complicated than doing something univariate. And therefore, the thing which usually happens is, instead of looking at the two-dimensional posterior distribution for mu and lambda simultaneously, to look at the marginals or full conditional distributions. And this is what all simulation algorithms out there actually provide you with. Every single one of them is doing simulations for the full conditionals, because that's what Gibbs sampling and Markov chain Monte Carlo sampling is all about. We don't want to look at high-dimensional distributions, because then the curse of dimensionality will hit us real hard for these models, especially when they get more and more complex. So looking at the full conditionals allows us to always look at a kind of univariate problem still. Meaning, we look at the mean and the posterior of the mean, given not just the data, but also the other parameter, lambda in this case. And then things are more or less fine, because our inference still holds. Now we have an inference which is only from the prior for this mu. And then we have a part where the data comes in, but not just the data, but of course also the other parameter. And along with the likelihood, the other parameter, which is part of the likelihood, naturally has to come in. And as soon as this is fixed because we condition under this parameter, things get a little bit more simple. And inference, again, provides us a closed form, a normal distribution closed form. And similarly, it does the same thing for our gamma posterior. As soon as we know about the mean mu, it's easy to obtain the parameters for this gamma posterior. Whereas doing it simultaneously for mu and lambda would be hellish. Well, in this case, it would still be doable, just like the 5 pages exercises all the guys in the math classes are scared of. But it's doable, but there are cases where this is simply not possible anymore. So how to use this idea of only looking at the full conditional distributions for algorithms will be our next question, and I'm going in the wrong direction. So MCMC sampling, KIP sampling, is all about full conditionals and only looking at these marginals instead of the high-dimensional problem. So MCMC is Markov chain Monte Carlo. Markov chains, as a quick reminder, specific type of dependency, because this is time dependency where the next value only depends on the previous one, but not the ones before. Monte Carlo sampling is a very general framework of sampling, which basically is meant to be scalable also for high-dimensional problems through some asymptotic approximation. In our case, the thing we want to asymptotically approximate is the posterior distribution in some way, and this typically happens by simulating samples not from the actual posterior distribution, but from these full conditional distributions of the posterior, and in this way obtaining samples which represent the actual posterior distribution by looking at all the marginal distributions simultaneously and in every single step. So there are several types of MCMC samplers out there, and I will talk about the two most relevant ones, the ones in the beginning first, and in more detail, and I just want to make you aware of some other terms which are out there in case you come across them when reading into the help files of the algorithms and stuff like that, just so you know what it is they're talking about. So Metropolis-Hastings sampling is the basic backbone of Markov chain Monte Carlo sampling. It is a super universal scheme because this is the adaptation of the accept-reject algorithm for the Bayesian posterior marginal sampling. This is nice, but it's tough because acceptance-rejection sampling is inefficient, usually. Acceptance rates are typically not 100%, but far lower than 100%, depending on how good your propositions are. So this is something we want to do only if we cannot find something more efficient. And the most efficient thing, and that's why you have the term Gibbs sampler in so many of the algorithms, JAGs and BUGs directly use them. They are the Bayesian inference universal Gibbs sampler and the just another Gibbs sampler abbreviations. So Gibbs sampling is the thing to do, but it works only for specific scenarios, and that's conjugate prior scenarios. Because then this algorithm becomes much more simple. And we will take a brief look at this, just because I'm a mathematician, not just by heart, but by training as well. So you will have to look at a few formula before I let you do the actual sampling, which is more fun. Awesome. And then there's reversible chunk sampling and both and death sampling. And this is something different, and this is one of the things where algorithms out there are truly struggling, because both of these are changing dimensionality, meaning from a higher to a lower dimensional or from a lower to a higher dimensional space. When would that ever happen to me? For example, when I switch between a normal distribution and the student t distribution. Because from the Bayesian perspective, the student t distribution is a normal where I do rescale the variance in a very specific way, such that the tails get heavier without losing the symmetry. And this means that I have to add these rescaling factors. Oh my gosh, all of a sudden I have an additional parameter which I didn't have before. It's changed the whole problem, the whole likelihood is changing dimensionality. Or another thing where this is coming from is mixture modeling or clustering, because we don't always know what the right number of mixture components, what the right number of clusters would be. So when we see that the number we currently have is not sufficient, creating another one, adding another one, creating this option to fill another cluster, another part of the distribution, is giving birth to another part. Or if we see, okay, we have too many components, actually two of them fall together, we want one of them to die, and then the rest of the samples to fall just into the one that is remaining, because then it becomes identifiable again. So these are scenarios which are very specific, but which can actually arise. And typically the word hybrid sample in this context means that you don't just have a pure Gibbs sampler, because this is the backbone of almost everything, but you add Metropolis Hastings components and you add reversible jump components. Then the whole thing is called a hybrid sampler. Good. So what's the idea of all this? So we want to obtain samples from the posterior distribution without actually having the high dimensional posterior distribution available. And we do this by constructing a Markov chain. So something where the next value will depend only on the previous values, and in this way obtain samples from this distribution, the posterior, which we do not actually know. And we do this by applying this Monte Carlo simulation scheme. And the goal for Bayesian analysis is to obtain samples from the posterior. So Metropolis Hastings requires us to have, even though we don't know what the posterior is, because it's not the closed form anymore, we can do the calculations by hand as we could yesterday. But at least we have some target density which we want to aim for, and we need a proposal density which is smart enough to allow us to propose a new value based on the old value. And in order for this to work well, we want two things to happen. The algorithmic thing is it should be easy to simulate from. Don't propose from anything which you cannot just provide random samples from. Even though it might be mathematically cool and smart, it's not algorithmically smart. And then there's a symmetry requirement. It has to work in both ways. If I provide you one value, and this is the one proposed, it should also be possible to propose the other value given the one which is the correct below. This symmetry requirement is necessary for the acceptance probability so that we can cancel this out. Why? Because this is appearing here. And if the proposal is staying and it's not working symmetrically in both directions, things get really difficult. And things get really inefficient. Because if it works just in one direction, like proposing from the tails but never getting back to the center, or only proposing from the center but never being able to move to the tails, you will have a problem. So you need something which works in this symmetric way. We will look at the Metropolis Hastings sampler afterwards. You will simulate through one and see how this acceptance probability is affected by choosing smarter or less smart proposal distributions. But this is actually what is happening in the background. So it's super complicated. Let's agree on this without doing the detailed math. Things get a lot better when we use when we do use for the proposal stuff which contains the likelihood and in addition its natural conjugate prior, because the target we are aiming for and the proposal we propose from are super simple, because then the proposal distribution is just the full conditional one. And as we saw before, as a brief reminder, the full conditional distributions, if we stay in this natural conjugate setting, we can still obtain an enclosed form. So if we can still obtain the full conditionals in closed form, we naturally obtain the reasonable distribution to propose the next sample from, because that's just the full conditional when I fill in all the other parameters. Whatever the previous value or the current value is. And in this way, I don't have to think about what would be a reasonable proposal distribution, how do I make this symmetric, how do I obtain efficiency, how do I make the acceptance rate large enough, because it just accepts 100% of these things, and that's what makes skip sampling so powerful and so advantageous, because the GIP sampler requires that we have at least 2 parameters, unlike the Metropolis Hastings sampler, because that one can also work with just a single parameter of the posterior, which we want to estimate. So we remember from yesterday, we had, for example, the binomial scenario, where we only were estimating the proportion and nothing else. There was no other parameter. For this kind of scenario, it's impossible to implement the GIP sampler, because it has this switching between the full conditionals, requires that you have at least 2 parameters which you are simultaneously estimating. This is important to know, because if you try then to work on this problem with any kind of GIP sampling algorithm out there, it will fail, because it can't do that. Okay? Whereas Metropolis Hastings, because it has this acceptance probability anyways based on some proposal distribution, never mind, it just works with 1 dimension as well. It doesn't require a second one. But the GIP sample is always multidimensional and therefore always requires at least a second parameter. Just to keep that in mind. That thing was proposed in the early 1990s, and this was really breakthrough for Bayesian computation, because now it was possible to tackle high-dimensional posteriors and high-dimensional problems. And the high-dimensional problem is already a linear regression problem, because we were looking yesterday at linear regression, and we saw that, okay, we already have to have one estimator for the one-dimensional slope and a second one for the residual variance or the residual precision. If it's not just simple linear regression, but multiple linear regression, then for every dimension you add, you have a new parameter to add. So this problem immediately becomes high-dimensional without being any more complicated at all. And therefore, even simple regression problems require that you have an algorithm which can work on this. And this is the power of this full conditional approach, because in this way this thing works straightforward. It doesn't matter what these probabilities are. We were looking yesterday at a lot of natural conjugate prior scenarios. So I told you for the Poisson distribution, for the binomial distribution, for the multinomial distribution, for the negative binomial, for any type of exponential gamma distribution, for normal distributions, we always have natural conjugate priors. And wherever you have these, you always are able to obtain a closed form posterior. In this case, it's not the closed form posterior, but the closed form full conditional. So the marginal posterior, just one dimension of the posterior distribution. Given that all the others are fixed. Not caring about all the other algorithms, all the other parameters, because I just plug them in based on whatever starting value. So in this way, I can simulate each of them from a closed form distribution, which is simple enough to obtain, whatever it is. And as soon as I have this one, I can plug in this new value. And for the other ones, that's why it's a Markov chain approach, I build it on the previous value of the specific parameter coefficients. And at the end of this scheme, it's not based on the previous step anymore, but it's based on the current step in the final, for the final parameter within each simulation, whereas for the first one, it's always based on all the ones from the previous step. This is the Markov part, this t-1 here, in the MCMC, in the Gibbs sampler. And in this way, it really does matter how large the dimensionality is, because each of these is a one-dimensional problem. And each of them, therefore, scales down to just the univariate distribution to sample from. Why is this relevant? Because it's much easier to obtain random samples from univariate distributions than from multivariate ones. If you ever did random sampling, this is absolutely relevant. When you can stay in a univariate framework, you want to do that. Yeah. And then here it says, first k observations of each chain will be discarded. This is weird, and we will talk about some properties of these algorithms, and we will also see why this discarding has to happen. This is called burn-in, because you start here from whatever initial value. Just plug something in, which will hopefully work. What will happen? It's a Markov chain, where we accept the new value in every case. But, of course, depending on where we start, we might start far away from the actual posterior scenario which we want to obtain. If, because it's a Monte Carlo scheme, where we add up all the samples to obtain, for example, the posterior mean, and we know that the mean is not robust with respect to outliers. So our initial value and the first values of the chain automatically are outliers unless we were lucky and already started exactly in the posterior side. This is a problem because it would bias not from the base estimator bias, but from a simulation perspective would bias our analysis results. And therefore, these first steps of the algorithm, the first simulations, have to be discarded, and that's the so-called burn-in. Yes?
Sorry, so I was just thinking two things. So what if you have a small number of steps? So is it a standard, like the removal of the first observations? Is it a random number? Is it predetermined?
You determine it.
Okay, and so what if your number of steps is somewhat reduced? So in the sense that your first of the K observations, they are removed a big chunk of, like a proportional big chunk of the information that you are simulating.
You're choosing how many you are removing, and you don't want to like shoot your own foot by removing too large of a proportion from your simulations anyways. So there's two ways of approaching it. Almost all the algorithms out there, never mind whether it's STAN or JAX or some other MCMC predefined algorithms, allow you that you specify this number before running the algorithm. But before running the algorithm, you might have no idea how many you want to discard. So there's always the option of not discarding anything at all, just obtaining the whole chain. And then looking at the traces and then seeing, okay, do I have to remove only the first 10, first 100, or the first 1,000? And when you realize, oh, I did 2,000 simulations, I have to throw away the first 1,000, then you might have to do this simulation again. Or you might have to rethink your starting values instead before running the simulation again, because afterwards you have a pretty much better idea, hopefully, once you know what's happening when the burn-in is over, where the actual values might lie, and therefore you can start closer to these values to also reduce this burn-in. So from an algorithmic perspective, it's simpler to do this in a few steps and moving closer to the actual scenario, especially when you need a lot of simulations. And it's a very high-dimensional problem. Yeah, but this is not super simple, so we will definitely look at these trace plots to get an idea of how long is this burn-in period, how do I recognize when it's over or if it's not over. Yeah, because this is one of the most relevant things to know and be aware of when working with MCMC algorithms. Good. I hope I didn't forget anything. Maybe it comes to my mind later. Good. We're returning to the thing we had before. So this was where we started out with our directed acyclic graph. We had our marginal posteriors, and in this way, this Gibbs sampler naturally arises when we do the simulation of the mean based on the previous mean, in the previous step simulated precision, whereas the precision can be simulated based on the value of the mean which we obtained in the first step. In this sense, this is a Markov chain problem because we have to rely on the previous step. But here, since we already have simulated this within this step, we use the most up-to-date information at all time about each parameter, and therefore this is only the full conditional and does not have this Markov chain reliance anymore. Good. So what's out there and what's actually using this? So based on these MCMC schemes is STEM. It's not the classical MCMC algorithm which is happening there, but it's Hamiltonian Monte Carlo which is happening there. But it's still working with these full conditionals and therefore still working within this Markov chain Monte Carlo framework. Then there's Bugs and Jacks, which already contain Gibbs sampler within its name and therefore tell you very clearly what they are originally intended for. With these two, you really have to watch out because you will be specifying these model scenarios for Bugs and for Jacks. And it works if and only if you have been taking care of keeping the natural conjugate prior. Because it's not really good at doing these Metropolis Hastings schemes automatically. Because then it would require additional knowledge of a proposal distribution, which you do not automatically do. Then it might just take the prior which is specified as the proposal. The prior might not be a smart proposal for the posterior. So things get super conflicted with this Bugs and Jacks as soon as you have not been taking care of properly keeping these model properties of staying with a natural conjugate prior framework. This is why I gave you yesterday these slides with for discrete and for continuous distributions what would be natural conjugate priors for the most common cases, because that's what you really need here. And then there's a lot of packages out there. We will look at one of it, the MCMC pack, which already provide you with pre-implemented samplers for various scenarios. And there are a few methods which do something completely different. Oh no, come on. One of the more prominent ones is INLA. INLA stands for Integrated Nested Laplace Approximation. And this thing does not do anything with Markov chains or full conditionals. Instead, it does integration based on Laplace transformations, and it works only for very specific scenarios, and that's Gaussian processes. Anything that's not based on a Gaussian process cannot be solved with INLA at all. And then there's the the new cool thing for all the real Bayesians, and that's approximate Bayesian computation. This is a really tough thing because here you can basically do anything. Doesn't matter if your posterior is high dimensional or low dimensional, if you have closed forms or not, if you use conjugate priors or not. The only thing you require here is that you have some smart summary statistics from your posterior, which you can easily calculate based on the data. And as soon as you have this, you will have to choose. We were talking about it yesterday, the loss functions. And based on this, provide a reasonable loss, which will tell you, okay, is the thing which I simulated here close enough to my summary statistics based on the data itself. Then it might be smart what I simulated, and then I keep it because I think that was from the real posterior. Or is it so far away that I will not consider this at all? This is really tough how to choose all the algorithmic details unless you're really well into the whole Bayesian theory, because it's not obvious what to choose as reasonable summary statistics here, and also not obvious what to choose as reasonable loss functions here. Okay, but that's just to give you an overview, because we will mainly focus on the Stan-Bax scenario on Markov chain Monte Carlo sampling, and we will also look at Inler for one of the examples, for a regression example, because that's where it still works. Good. Now, work starts for you, because it's a workshop and you're supposed to work and not just me. So I tried to provide you all the codes, all the examples which are happening from now on, so that it's easy for you to follow along. And that's what I'm kindly asking you to do now. So we will go back to our body sizes example. We remember we had this normal distribution scenario with the mean of 175 and the sigma of 14, and we were looking at normal distributed data simulated from this. And now here we will look at different prior scenarios. So the first prior scenario would be what is considered a non-informative prior scenario. So when we really have no idea of the mean of a normal distribution, the best thing to choose is 0. Then we're non-informative. When we also choose a rather widely spread variance for this normal distribution, and therefore make it rather broad prior. In this sense, it's weakly informative. And then this is the choice of 0.5 and 1 for the lambda inference, for the precision inference. And I provided you with a second set of these later on. But when going through this with the simple Gibbs sampler, which is simulating the value of mu based on the other ones, and then the value of the sigma squared based on the other one already predefined, with 10,000 simulations, and in this case we only throw away the starting value and keep the whole burning to take a look at what's happening here. So I simulated data around 175 but my posterior is located more or less close to somewhere between 160 and 165. Okay, now we get an impression what it means that the Bayes estimator is biased, because this bias is happening because of my non-informative prior. Why? I'm telling it, you know, I expect it to be at 0. And then it's actually around 175. But still the 0 information which I give it from the prior draws this posterior in the direction of the 0. And in this case, causes a bias which is large enough for us to still see, which is not nice. A little bit disconcerting. So the second thing is these trace plots. Here, the Gibbs sampler is working pretty well in that within the first step it gets to the correct value, and here it's just dropping down to 0 because I didn't remove the last value anymore. And you can see that we do not see any burning. It's immediately going to the right value, and here only for the first one we see it has to go up, and then it's more or less behaving stationary. So this is an algorithm which almost immediately blends with the correct posterior without having to remove any burn-in at all. So throwing away here the first 1,000 samples would really not help me at all. It would only make me lose something I invested computational power in. So sometimes just keeping everything and really looking at these traces to get an idea what's really happening, and if this algorithm is converging much faster than I originally expected, might be a smart idea. So let's look at the relevance of priors. Let's be informative now. I mean, it's human body sizes. Who expects the average human to have an average size of 0 centimeters with a standard deviation of 100 centimeters? Yeah, ever seen the small dwarf with minus 100 centimeters body size? So yeah, it might not have been a smart thing to do. So let's use information. We change only the mean. We keep it non-informative in the sense of still keeping this very, very broad distribution, but now we don't center it at 0, we just center it at 170. Because even though if we don't know precisely from whatever what the previous body size, what body sizes might be, but 170 sounds smart enough. Let's say it's. I keep this one identical. And now we're good. Now we're actually landing much closer to where we would want to land. We still shifted a little bit toward the 170, a little bit downward. It's not actually symmetric here. And this is not actually the peak around 175. But now we are not drawn away by like 10 centimeters downwards. Not shifted as the whole posterior. But something is still not fully right with the sigma square. Again, the trace plots say, don't worry, it's perfectly fine. There's no burn-in still necessary to discard here. Only like the first and the last value. Yeah. what I would like you to do is here, for example, wrong direction, not so good with this pointer thingy. See what happens when you change the prior precision, make it more or less precise, what the effect of this is. See what changes if you change the prior parameters for the variance, for the precision estimation, whether you can get this to being actually closer to where it should be, because this is all relevant apparently, and it's meant to give you some idea of how choosing the priors will affect the outcome. And what we are doing, what you are doing here is the so-called sensitivity analysis, getting an idea how sensitive the posterior distribution, the outcome from the Bayesian inference is toward, choosing the prior distribution. And if shifting parameters just a little bit has a large influence on the outcome, then it's called sensitive with respect to this prior parameter. Then it's really relevant to make sure that you move in some way towards something which either you can justify from theory, or where you obtain a suitable large enough interval of such prior choices for one of these parameters, where switching it a little bit does not have too much of an impact on the posterior distribution. Because otherwise, the algorithm will depend mainly on your choice of parameters here. When you're not even sure what you're doing here, it might not be smart to choose something which is super sensitive. So create a vector or a sequence of different values, trying them out, try out simulations, because this scheme is so fast that you can easily simulate it within a few seconds, and therefore look at the influence of these different values directly. Good. I'll give you this chance for playing around, and I'll go around if you have any questions to answer to you. Yes. Because on the first slide we have the otherwise it's super complicated. No, I feel like that's why it seems as she needs to be clear in the slide, because I would
So how do we choose the prior within an interval where it's analyzes like around the mean? Because here we know the truth, but usually we don't.
Yeah.
So here it's easy to choose.
Exactly. So it's about finding an interval where it stays stable, and you know that it's not sensitive with respect
But then you also
because otherwise it's computational sensitive, and that's really
So when you doesn't think about reporting results from the analysis,
I know which are the relevant parameters for shifting this. So then,
the thing also is combine this DNA analysis.
sometimes it, yes, depending on whether this is really a map or not. But,
Because here we're thinking about the case where we don't have any information, we're trying to find give something. But if you already have prior information from elsewhere, you don't
then
need,
it makes sense, then you don't need it.
you don't need the
Really
sensitivity analysis.
well-founded
Yes,
prior,
right.
but for example, for the inference for the precision,
Yeah.
you never have too much prior information.
You
So
can,
maybe you have prior information on.
But should we not also look besides the trace flows to the summary statistics and see how they're stabilizing as well when we
Yes,
just move the bars around?
this now,
Yeah.
also the shift from the value it's supposed to be.
Yes.
And then you
Sure,
get
more detailed analysis, because that's just young and impression and having something to work on now.
Yeah, I don't understand. I was just wondering
Yeah.
if we would have to.
Yes, it would make sense, yeah, to see, especially to see when I'm only looking at, I don't know, the posterior mean or the posterior median, how much this is shifting, because this is hardly shifting at all.
Yeah.
Even though the shifting is okay,
It's fine.
much, it's fine, but this is within this range, but as soon as this is shifting a lot, then you have a problem. Yeah, so I was really happy to find this example anyway, to see completely the breakdown of the mean, even with 5,000 samples versus the prior.
Yeah, for sure.
And we also have a new guide here who volunteered yesterday.
Yes, we do. Where is he? Would you like to? Maybe. Oh, I know him. No problem. Doesn't take me away.
Let's see, everything here, which one? Usually 100 and 3 so we can compare.
What is the? Yes, yes.
Basically,
Okay, so
this is for but it is the same, so we use this one.
No, I didn't want, so it's the one.
Okay. It gets smoother there. No, it doesn't affect
So how would
It's really bad. It's like that.
o que é que tu podes mudar são as parâmetros de informação anterior. Começar com zero e descrever agora já queres pôr aí algumas informações sobre os passados. Por exemplo, depois
Temos que a cultura de todos as pessoas não é desse
mas podes variar e depois na parte da precisão, tu na realidade, como sabes como é que chegaste aos dados, neste caso tu até sabes qual é que é a variância que tu tens, não é? Tu puseste transferir o padrão de 14 e tu aqui nas periódicas estás a usar o desvio padrão de 1. Estás muito boas resultados. Não giraste os dados. Não. Aqui fez as coisas que muitas vezes não está assim, mesmo assim, aqui estás a gerar os dados. Sabes que a verdade é sabes que a verdade é padrão é padrão. Portanto, quando tu começas aqui no priori de padrão 1, tu estás muito longe da verdade. Ok? E, portanto, se quiseres agora uma análise mais rigorosa, é tentar aproximar como isto é interativo. Mais próximo da verdade, mais próximo depois vais ficar muito mal. Faço estas coisas, deixa eu ver se eu tenho aqui no próximo mais aulas para mostrar. Nessas categorias
Doesn't take like yeah, I think I say that would be reasonable after our first thing, and then you can run it again. And you see, okay, now it's reasonable.
Tu podes começar com vários valores. Começar com o valor inicial. Exatamente. Independentemente, vais chegar no ponto onde vais conduzir isto estacionário. Obviamente, se tiveres mais filhos, vais melhorar a convergência. Portanto, terás que aumentar aqui ver coisas superiores. Sim. Demorou quase às 500, só começou a corrigir no 3. Comecei ainda mais próximo, ficou logo lá e agora é porque isto
Okay, what are you doing? With sensitivity analysis?
a distribuição, a cadeia estacionária, mas na estrutura. Não sabes qual é o valor. Não sabes. Por isso que ela estava a dizer, é que deves, quando não tens informação a priori, uma espécie de. A tentativa é tentar capturar onde é que está estabilidade. Quando não tens informação a priori, tu vais usar uma priori no informativo. Mas sendo uma coisa informativa, não é? Que é o mais correto possível, que é para todos os acontecimentos que mais ou menos aqui prováveis. Mas aqui também usa já uma uniforme, é uma linha assim que tu vais usar, uma normal, que é quase que uniforme, porque é muita chapada, porque estás a ter uma variância grande. Portanto, tu tens uma variância da normal, porque tens que ter muita chapada. Você não tu podes. Tu fazes, experimentas com várias métricas diferentes e podes prever o comportamento dos 13 hipóteses. Ou seja, aquela que está aqui, que agora já. Aqui, por exemplo, ela aqui começando em 0, nós mostramos taxa de estabilizar estas estabilidades longe. Tu tens que perceber entre valores, estas manchas vão sempre umas em cima das outras. Ok? Por exemplo, se tu vai começar com outro valor, se calhar depois a verde já vai dar aqui. Começas no outro valor, a verde, por exemplo, igual também vai dar aqui em cima. Quando tu arranjas uma baliza de valores, onde todas os 13 plots estão uns em cima dos outros, tu sabes que estás numa região que não tem mais parâmetros. E depois, quando tu vais ensinarear aquelas observações todas, tu pegas naquelas 10 mil observações que estão nas móveis, tu tens sempre a garantia que estás a estimar bem o teu parâmetro. Porque são muitas observações, portanto, isto chama-se a análise de sensibilidade. Pronto, mas depois tu também tens outras coisas, não deixas os 13 plots, tu também vês, isto é o 13 plot que eu tenho aqui para os alunos, mas tu também olhas para a média corrida. A média corrida é uma coisa muito gira. Tu, à medida que vais calculando, por exemplo, tens uma observação, a média dá outra observação, tens duas, a média dá a média das duas, tens 3, a média das 3, e se tu reportares as médias à medida que vais mantendo as observações na cadeia, interessa-te encontrar a boa mistura é aquela onde a média começa a estabilizar a partir de um determinado número de populações. Ou seja, não é só cuidado, então tem muito mais coisas. Não é só fazer este trade-off, não é só os histogramas, é mesmo fazer as médias corridas e há mais uma série de medidas que são utilizadas para ver a convergência das cadeias. E é muito cheio de isto, duas aulas disto não dá para ler.
Tu já deste,
Eu dou uma aula de 4 horas só de inferência e dou uma aula de 4 horas só de computação. É este também que aconteceu. São as 2 últimas aulas do semestre. Só é pouco tempo para isto, mas melhor que se pode.
Ana, tens que arranjar um tempinho para a gente falar um bocadinho.
Vai ter que ser esse,
Eu também não me importo, mas deveriam poder chatear em
não, mas deve ser.
Para mim?
Não, vai ter que ser em agosto, e eventualmente, se não der na primeira semana, tem que ser na última, não é? Tem que ser na última.
É o mundo.
Primeiro semana.
Não pode ser este mês?
Mas agora não consigo, eu já me vou embora para a semana. E para a semana, se calhar não vou chorar. Eu passo pela bandeira, tenho exame.
Mas quando é que voltas?
Volta ao 1 de agosto. Sem eu fazer coisas de antes, coisas assim, há quem nos faça assim, pensei, ok, vou ter que trabalhar na primeira, porque eu não fazer e agora vou ter que trabalhar no vídeo. Por isso não consigo mexer naquelas 2 semanas de recurso.
Também não pode haver aquela coisa, eu tinha que ver aquele trabalho na noite, porque eu estava também a fazer coisa até o Natal e tal, mas já deve ser cadeira. E ela disse assim, falava comigo sobre isso, mas tens isto mais presente, não é? Portanto, era...
Assim que eu fiz aos cenários, os materiais os materiais da marca e da Isabela, eu acho que tem um pouco, eu consigo enviar português, porque é organizado.
Não precisa, a sério, eu só queria ter uma ideia. Não, mas isso não sabe isso para passar nas coisas. Não tem problema. Eu só queria ter uma ideia. Agora estava a ouvir dizer, por exemplo, que isto são as últimas aulas do semestre.
São 4 mais 4.
Não é nada, não é?
Não é nada e
Fica assim uma lambiguela.
por acaso não fica.
Não sei se ela faz a qualidade.
Eu vejo a parte diferencial todas com eles, por exemplo, eu tenho aqui, deixa-me mostrar. Isto não é, eu estou precisando de acompanhar estes slides mais antigos porque eu aqui não tenho, material do ano passado.
Sim.
Deixa-me procurar aqui as cheias.
Okay, I have zero information.
Mas como eu vou dar a cadeira, não sei que eu vou fazer o mas eu fiz um curso para mas vocês não têm na SPEM, não sei se não é os cursos que eles fazem na e depois ainda fiz um trabalho eu sou muito pouco presente.
Esse também não, eu estudei isto. Exato, é assim, eu tenho as 2 aulas do livro de desenho. Primeira aula, parte dos 4. Segunda aula, parte 2. Esta é a primeira aula, esta é a primeira parte. É a concentração da disciplina de Fonseca. Okay? E digo assim, esta disciplina dada pelas pessoas este programa e nós vamos fazer isto tudo até aqui em 2 aulas. Mas é para fazer a integral da disciplina. Depois disso, se vocês quiserem satisfazer esta disciplina, podem profundizar. E depois começa a inferência desse ano. As comparações, a história toda que a Alex fez, só que com mais fácil. Exatamente. E as coisas, depois começa pelos piores.
more way
Os órgãos superiores, os calcular as possibilidades, a dificuldade, o código S, as expectativas as subjetivas, as consideráveis, as teoremas, depois vou ter alguns conhecimentos
E tu usaste sobre que referências que tu viram? Vocês também dão para é isso que eu também
eles têm melhor agora, não, 2019, o último da Cambridge University Press. Eu gosto deste. Pronto, este é só a primeira parte e são 79 slides. Sim, depois vejo aqui as piores conjugadas naturais, importante, faço aqui um sumário para cada família, quais são elas, normalmente o que é que dão, não é? O indicador da TDL,
para falarmos isso também mais apenas,
tudo não consegue ser para as 2 semanas, semana assim. O que é esta disciplina, pelo menos o que é que eu fiz mas eu agora preparei esta disciplina pela primeira vez, também que eu tinha estes materiais, mas eu
Good, folks. Let's have a look at the last few examples because we still have some more. Let's not get too lost here now. You can play around a lot more. You still have several days. You will keep the code for the rest of your life if you want. So no worries here. So I was just discussing with a few people different things. So what we saw is that for this normal distribution, on the one hand we have a much better idea what the hyperparameter is, as opposed to the gamma distribution where we have for this weight and shape parameter, we have a little idea what it actually is supposed to mean. And also we see that it's more sensitive with respect to the choice of the mean than it is with respect to the choice of these gamma distribution parameters. Or did anyone find anything else now playing around a little bit? This is more or less consistent for people. So the choice we made here for these gamma distribution parameters is less influential, and therefore we are safe in the sense that whatever we chose here, even if we don't really understand it, it's not the algorithm is not sensitive with respect to that choice, and that's mainly what we want to be protected against, that we are not manipulating results by a specific choice of hyperparameters. And just shifting away a little bit would make everything break down, but we chose these results because these are the ones we want to publish anyways. So that's mainly the goal of this type of sensitivity analysis. So next thing will be to look at the Metropolis-Hastings sampler. And here there are a few more things to be aware of. We are also now tracking the acceptance ratio of the mu, and in order to get some impression of how well this algorithm is performing, you will soon see why, and you will also see why it's the mu and not the sigma which we are tracing here. Why are you not reacting? Yeah. Again, you have the code on GitHub, so you don't have to suffer from the minimum output code. The acceptance rate of the mu is 0.0096. So if we round it up, it's 1%. of all our simulations, which we're actually accepting, whereas for the sigma, it's 90%, 90%. So apparently, sigma is not the thing which is worrying here, but for the mean simulation, we have the problem that only 1 in 100 samples is actually accepted. And all the others we're proposing and proposing and proposing, and it's not accepting 99% of our proposals, which is not good. And you can also see now what this means graphically. So the sigma, we see this rather nice performance running along where it is supposed to go. It's going up to the sigma, which we put in there, and nothing's too worrying here, and it's really moving around all the time, this Markov chain, and rather ever getting stuck as it is for the simulation of the mu, where we see that there are whole areas where it's staying at the same value, and whatever we are proposing is not accepted. So something's not working properly with the proposal here. And I chose this not so good proposal on purpose to show you, on the one hand, what here at least you can see some kind of burn-in phase. What it means that you have to shift at least in the direction of the right thing. I didn't choose 0 here because it would never go to the right value because it's so slow at converging here. And even though we started at 170, this algorithm still is not getting where it's supposed to get. So here, this is what the trace plot is really about. It's about tracing convergence of these Markov chains, because only when the chain has converged to a stationary distribution, the result of this MCMC outcome can be used. And therefore, taking a look at what it does and not just taking whatever comes out of this algorithm at face value is really relevant. Because this just takes like forever to shift anywhere. So here, the thing affecting this partially is the step size for the mu, because this is how the range within which new proposals happen. And if it's just too small, new proposals do not happen fast enough to allow convergence. So here, where is it? Oh yeah, no, that's just too small. I'm getting ahead from looking at it. Shifting around this thing, and also here the step sizes, has an influence on the proposal in the Metropolis Hastings sampler. And being aware of this thing, the acceptance rate, and tracing it is one of the really most relevant parts, as otherwise you will have a severe problem with not being able to obtain any reasonable outcome of such a simulation. I told you before, keep sampling was the thing that made MCMC powerful and widely accepted. Because before they had this, and this is super dependent on the proposal, it's super dependent on choice of step sizes, on whatever. You can't do in large-scale simulations with algorithms which have such a kind of performance. That's just not doable. No one would want that. And therefore, whenever you can avoid a Metropolis-Hastings step, this is not a fine-tuned one, but a really like super crude one to make it break down. We don't want to do this because you really have to invest a lot of thinking in how to do steps which are not working within this very nice closed form natural conjugate setting of the Gibbs sampler, where simply every single proposed value is always accepted. This is still okay with 95% acceptance, but 1% acceptance is just unacceptable. Good. So much for Metropolis-Hastings. In this case, breaking down intentionally to give an impression of what could go wrong. So, JAX. Just another Gibbs sampler has the advantage of having RJAX as a package available and allowing you to specify these models directly. And I told you that what I showed you before, you will have to directly write into the JAX sampling model. And this is where it's happening. So it iterates over all of the samples, and here specifies the normal distribution for the likelihood. And then we have these two parameters, and basically this is where the additional simulation comes from. This is the prior for the mu, and this is the prior for the precision, the gamma prior. And basically, in order to end up with something which is on the scale of a variance, we take 1 over this precision. Good. So in this way, this model is directly what we have seen before as the mathematically defined full conditional model. It executes the model here, and then will provide you with such an output. So we are mainly looking at it to get an impression of what to read out here. So we see it shows 2,000 iterations. I mean, it shows them so that it will not occupy your machine too long. And then there's a so-called thinning interval and sample size within the chains. So JAX does do parallel chains by now automatically, in order to make it easily applicable also for clusters when you have the option of going beyond 2 or 4 parallel chains as opposed to your personal machine. And you might, if this is a really, really large problem, want to use smaller chains to build up a large one as soon as you have reached convergence within each chain, because then they will all be from the posterior and can again be combined based on the usual Bayesian updating argument. Thinning is something else than burn in, and it's trying to cover a different kind of problem than the burning. So again, we have to keep in mind we're working with time series here. We're working with Markov chains. So there's always this one step backward dependence. But in the end, we want IID samples of the posterior distribution. but we're sampling from we're sampling dependent outputs. We're sampling from Markov chains, but in the end we want something which is IID. So this sounds like a contradiction. And if we, wrong direction. If we have something like this, we can see that in the end, when doing the Monte Carlo integration over all these samples, it will not matter. As soon as we left the burn-in, the first few observations behind us, we can just treat all the rest as if they were random samples, IID samples from the posterior, because we have convergence here. When we don't have convergence, things get problematic. They might also get problematic if they have this sticking behavior, like you stay to a value and you stay at it for 10, 50, almost 100 steps, because you're not getting a new one. Because proposal is so small. So the proposal, the acceptance is so low. And in order to help with this behavior, I get stuck at the value and it moves very slowly to another one, thinning exists. Thinning means we do not write out every single value, but we only keep every fifth or every 10th value. What happens then, because Markov chains have this one step backward dependence, if I keep every 10th value only, I'm breaking this dependence. And in this way, when there's this slow convergence happening, or even if it's not shifting, if this is the actual, it is converging, but it's just very slow at shifting to different values because acceptance is too small, then thinning helps me to not have too many values written out in my results which have just the identical value, and breaking this type of dependence out of the simulation. So this is what it is meant for, and this is why this automatically happens. Here it says thinning is 1, so it keeps every single value. We do not reduce it. And to show you the traces, this is totally justified for the algorithm which we have here. Nothing too bad is happening, neither with the simulated tau squared, nor with the inverse which we compute from the thing. So basically we end up with converged chains and therefore with reasonable posterior distributions from the Jack's algorithm directly. So it's perfectly okay that we didn't do it. Why is it relevant to specify this thing in advance? By running like a small-scale experiment and learning which of them might have a problem similar to what we saw before with the pulsating sampling simulation of the mu, where we have this very slow convergence happening. It might be reasonable and also computationally, or from the memory perspective, much more efficient to not keep every value, when I know from the small-scale experiment that it will be super inefficient anyways. So let's just keep every 5 or every 10th value and throw away the others, because then they will not block my memory. When I need, in the end, a chain of length 2000, because that means I have to simulate 10 times 2000 values, but I only store the 2000 because I keep every 10th value only. So in this way, thing is relevant when I'm aware, wrong way, when I'm aware that I have problems like this, staying longer on wrong value or having a very, very slow scale convergence. Good. How am I doing with time? Okay. Good. Then Stan. That's the latest one out there. You will need C++ on your system in order to run it properly. Stan has been developed now for at least 10 years, I think. And it is not the classical macro-chain Monte Carlo simulation, but it's Hamiltonian Monte Carlo. It still keeps this notion, this Gibbs notion in the background, but it's based on just a different type of algorithm. And making the simulations more efficient. And what it also has, what few packages out there have, is it has a professional crew of computer scientists who are only working on implementing that thing. So this is not just some package which one researcher or a professor with a small team of PhDs and postdocs implemented because just they like it and that's their baby, just as JAX or IMLA are. But this is Andrew Gellman's pet project, and he has the money to hire dozens of computer scientists to do really professional implementation. That's why this is the best code which is currently available, the most up-to-date code currently available, and the best quality of simulation results you could possibly get, because it's computationally much more efficient than anything else you will find out there. So if computation times are really relevant, you want definitely to go for STEM. Good. So much for this as the first implementation. Oh yeah, it's just so long that we don't get in here now. Please do run that thing for yourself and don't have any plans for the next 5 minutes for your machine, because that's how long it will take to actually do these simulations. So it's doing 4 chains here, similarly to JX before, and you can already see it's telling you how far it has gone within the total sampling. It's using here a so-called warm-up instead of burn-in phase. In this case, discarding the first 1,000 samples out of 2,000 samples, which might likely be far too much, but it's not really caring too much, and it also gives you some idea of how long it will take. So these so-called leapfrog steps, which are specific accept rejection steps, 10 of them take 0.66 seconds. So for 2,000, you can just do the calculation approximately. So yeah, just have no plans for the next 5 minutes for your machine. Yeah, adjust your expectations accordingly. You have been warned.
What's the tree for the sampling model? The line above the chain one.
Which?
The sampling for model 917.
Yeah, that's some internal code of what this model is within your machine, and it's creating that, I don't know.
Does it store? So would we with that information, would we be able to just run a whole bunch of different models there?
If I were a better computer scientist, I might be able to answer it. I don't think I could do it. I just store the model, output in the usual R variable way, and did not try around with any other stuff because I have no idea how to access that. Sorry. Good. So we have about 20 minutes left. So we go through several of the algorithms again. Don't worry, you don't have to do Gibbs sampling and Metropolis Hastings sampling again. That was too shocking. I just did it once with you so that you can appreciate all these nice packages out there doing this hard work for you. We look at email data, which likely many of you will be familiar with. Yes, no, I don't know. Some of you have seen this. So this is one of the most famous data sets for diabetes research. The last variable here is the intended outcome of this whole model. It's whether a person suffers from diabetes or not. And it was performed, I think, in the 1960s, plus minus 10 years, with several women, several hundred women of the Pima Indian tribe in the US, because they noticed that they have a rather higher than average chance of suffering from diabetes. And therefore, researchers thought it might be a good idea to look at the whole of them and get some impression of what's happening, what's causing diabetes in these women. So it's all women, which is also the reason why the number of pregnancies is a variable in this data set, as well as glucose levels, blood pressure, the thickness of skin on your upper arm. So someone with a lot more medical knowledge than I can tell you how this is related to measuring body fat or something like that. Then there's the BMI, at least that thing's famous. Pedigree is relevant, how it's a variable decoding how likely someone else in the family has already suffered from diabetes and how closely they are related to the person. And then this is based on those factors and is something between 0.0078 and 2.28. So it's definitely not the number of relatives because you hardly have ever had 0.007 relatives in your family. The age is pretty clear, and then this is the diabetes outcome. So to visualize this data, the intention is to do a regression, in this case logistic regression, not classical linear regression, because the outcome we are aiming for is a 0-1 outcome, whether you suffer from diabetes or you don't. In order to give you an overview, I provide you here with the histograms. Here you can see how the relation between some of these variables look like, and in the end, what is relevant or not relevant is how these things are correlated, because it's a regression setting. What's truly bad is if our actually explanatory variables do have linear dependencies, and the truly disturbing linear dependencies are age with number of pregnancies. Who would have guessed? And therefore, only age will stay in our model, because that's the one thing we rather know more, or we have rather reliable for almost every human being. And then BMI and this skin thing apparently are highly correlated, so I still don't know what exactly it is, but it's really well working with the BMI, and therefore taking care of this body fat measurement in some degree, but it makes sense to keep the variable which we have more easily available, and that's the BMI, because you all know what your skin fold thickness is, of course. And you could plug it into the model to predict your diabetes chances, so let's stay reasonable and take that one. Good, so this would then be the reference analysis. We take a generalized linear model. We are staying with a binomial family, making it a logistic regression model. We kick out the number of pregnancies and this skin fold thing, and we want to model type, which is the diabetes yes or no thing. Then we end up with a lot of stuff. Intercept estimates, glucose, blood pressure, BMI, pedigree, and pH. We see, except for the blood pressure, everything's more or less relevant. Good. So this is the base model. It's just here as a reference. Also to provide us with estimates for the coefficient of this model as a reference, because we will compare Bayesian estimates against these one in the steps to follow. I'll stand the Hamiltonian Monte Carlo thing. So Hamiltonian is actually from physics, from computational physics, and we do approximate numerical integration with that thing. To give you an overview, there are lots of packages by now which work based on STAN. And RSTAN ARM is the one I really want to show to you now, because RSTAN ARM is applied regression modeling with STAN, and this is among the most frequently asked inference problems and questions which we want to do, and this provides us with all the standard regression settings, especially with something which is similar to the GLM, which we've just seen. And the good news is it also keeps this R formula notation. This is really something you will start to appreciate once I show you some of the other algorithms, where you don't have this nice formula notation anymore, and then you can start crying and things will not be so nice anymore. Yeah, what it also shows you, except for what we already know, the formula we want to simulate here, the data which we have is based on the family, which is the binomial family, again for the GLM. So this is identical to what we have just seen. Then there's the priors. We're still Bayesians here. So in each case, you specify the distribution and its parameters, basically based on how R is doing this. So for the intercept, we use a normal distribution with 0 and 10, as opposed to the prior for all the coefficients which have smaller variance, being around 0, also centered around 0. I was talking at the end of yesterday's workshop about regression and thinking about what the effect of these prior precisions or prior variances on the regression problem might be. So with the intercept, typically we really want to allow a lot of things, because this is when we don't know in advance where these values and outcomes might lie, something where we really want to allow a very wide spread. So even a standard deviation of 10 might not be enough, typically, But here we don't care whether it's 0 or whether we go away from 0. However, with the slopes, with the coefficients of the regression, we do care a lot more whether they are 0 or not. And by choosing a smaller variance here for the regression coefficients, we kind of enforce the model to be closer to this, the coefficient is 0 setting, and only move away from the 0, which is our prior information, when we really have a slope which is non-zero. Zero slope means that the parameter is not relevant, means that there is no linear interaction, and making this thing smaller enforces sparsity and enforces shrinkage of the regression coefficients. This is really something to keep in mind and to be aware of, that in this way, making this larger or smaller, we can allow the slopes to go away from 0, far away, which might be reasonable for some regression problems, where we do need a big slope for whatever reason. But if we really wanted to be more sparse, to shrink the coefficients, then it makes sense to enforce it to stay like closer to the 0. And only when you have information far away from 0 to really remove this parameter value, the coefficient value, away from the 0 scenario. And the last one is for auxiliary variables, so they're using in the background auxiliary parameters, which is based on a Cauchy distribution. This is a super peaked distribution, basically the t-distribution with degrees of freedom equal to 1. So super heavy tails. And because it's a heavy tail distribution, you can keep it in the background as an auxiliary background variable to take care of any non-robust behavior. And the rest of the stuff is again number of chains, number of iterations per chain, and you can also provide here directly a seed if you want to set a seed and make your results comparable and repeatable. Good. Tells you that, okay, it's 1,000 draws here, and after the warm-up, it's kept at 4,000 ones with a warm-up length of 1,000 per chain, and therefore for 4 chains, throwing away out of 2,000, 1,000 each makes 1,000 times 4, 4,000 draws to consider as draws from the stationary distribution. The thinning here has been 1. We did not reduce any dependence here. What it automatically does is provide you not just with the mean and the standard error of these means, but also with the quantiles of the posterior distribution. To give you a good expression or a good impression, the median as compared to the mean, the 25 and 75% quantiles, and also the 95% highest posterior density interval. Because these are normal distributions. The posteriors are normal again Therefore, they are symmetric and providing you with the 2.5% and the 97.5% is automatically giving you the lower and the upper bound of the 95% highest posterior density interval of these estimates in the normal distribution case. Good. Then there's this thing here, NF. NF is something which comes automatically out of the post analysis, and it also explains what exactly it is. This is the so-called effective sample size, and you can see that for each of these you have a different effective sample size. I was telling you before, we want to do thinning to get rid of this dependence within the time series, the simulations. Effective sample size basically looks at, okay, how many of these are really different and are not too much dependent from the previous value to the next value, so that they are really effectively IID, independent and identically distributed. Independence is the crucial thing here. So for glucose, for example, we have 6,400, not out of 4,000, but out of the total 2,000 times 4, out of 8,000, which would have been the effective sample size. So 2/3 more than 3/4, more than 3/4, more than 75%. This is nice. This is one of the good ones, where basically you know that 3 out of 4 would really be IID. And then there's the not so nice ones, like the BMI, where I have this reduced to only 3,200 out of 8,000. So this means 2 out of 3, more or less, have this dependence problematic. So here, in order to work with that thing properly, you would have to thin the chain and keep only every third value to really break this dependence. Because there are real amount of chains, and here, unlike the Metropolis Hastings sample, we keep every sample. And therefore, throwing away 2 and only keeping the third one, we break out, or we break this dependence behavior, and it's just not enough to throw away every second one as it would be here, or 14%. So this is what the effective sample size tells us. It would have been really terrible if we would look at the effective sample size for the Metropolis Hastings sample, which we had before, because then you could divide the number of samples by 100 in order to obtain the effective sample size, because this was the acceptance probability to even give us that. So this is the reduction, or what we actually can keep as really independent samples and consider as independent samples. And this is far less than the number of samples which we have actually obtained and simulated. And therefore, this is a very reasonable measure for the quality of the algorithm you have just performed here. And it's good to look at that. Yes?
Here, if we have some dependency, what is the danger? Is it that we estimate all the new values, or just the confidence interval that is going to be affected? Versus, if we keep like this dependency issue?
It depends what you want to estimate. So if you just do like a posterior mean, and you sum up all the values and divide by the number of values, never mind dependencies. Who cares? But if you really want to get a better impression of what the structure of the posterior looks like, if you want to do predictions from this posterior, then it starts to affect us, because we do not get this very independently, but there is some structure based on whether I take the first 1,000 samples or the next samples from 2,000 to 3,000, because there is dependence within each of these. And then the structure of the posterior might actually be affected, and this affects also the size of the density in the walls. But in particular, it will be terrible for predictions. So when prediction is my goal, I really have to take care of this. When I only care about the mean, never mind. Yeah. So it really depends on what kind of question we are asking. Good. Yeah, so just to finish this, our STEM-arm also provides you with the plots of the posterior, or at least the box plots of the posterior parameters. As you can see, it's super inefficient when these are all very close to zero, because you can see super large points, but you can't even see the box anymore, which is not helpful, which is why these intervals have been a lot more helpful to tell us whether it still includes the zero or not. But for a brief impression, it's really good. And since we're already almost at overtime, I'll only briefly introduce you to one thing which is different from all the other ones, and that's INLA, Integrated Nested Laplace Approximation, because this is unlike Markov chain Monte Carlo, which would, even though it's simulation based, it's not biased with respect to the outcome of the posterior of the Bayesian model. Whereas INLA is only approximate Bayesian, and therefore if the Bayesian estimator is already biased with respect to the maximum likelihood estimator, and this thing, approximate Bayesian, is biased with respect to the actual Bayesian model, because it does some simplifications. And these simplifications is it assumes certain independencies in additional in order to be able to perform numerical integration. And INLA is based on doing numerical integrations in order to do the approximation. This makes it deterministic, but it sacrifices some of the unbiasedness for this. What makes it cool is that because it's deterministic and only doing numerical integration, it's much faster than these MCMC algorithm schemes, which have to do thousands and thousands of samples in order to give you some idea of the structure of the posterior distribution. So this is fast. However, it works only for everything that is latent Gaussian in its structure, which at least is the case for all regression problems. And therefore, it's widely applicable for standard problems, but not for anything where you want to move away or where you want to specify priors which are not within this standard setting. Yeah. At least what INLA also does is it works with the standard formulas. But I told you before, you will start to like the nice notation of R stan R, because here you have to manually start to split into the numerical form of your output variable and the x variables as a matrix So here we have the problem that we need the model matrix as one input, and we need the vectorized numerical form of the y's as the other input, because otherwise this algorithm will not work at all. So now we are in the real numerical part, and this is just taking out the two variables which we were taking out before, the skin and the number of pregnancies, and taking out the target variable as the columns which we don't want to include. Yeah. Basically, we end up with something pretty similar to what we had before, and it also provides us with the standard quantiles of the posterior with the 95% HPDI and with the median in comparison with the means. Good. Yeah. So much for that, so that you could at least briefly see in there and get some impression. I'm again already over time, so I'm sorry, still keep you from your lunch, but I hope you will survive it. Thank you for being here. Thank you for all your interest in Bayesian inference and participating very actively. Yeah. I did all the talking, but you did all the coding, so it was perfectly fine this way. They were all doing a lot of stuff in between when I sent you out with this deep sampling example. So yeah, it was really nice workshop, and hopefully we have the chance to meet at some point again.
Thank you.
Thanks.
Okay, so thank you everyone.